Now let's go back to the same contingency table we used earlier. Now let us suppose that the patient we sampled is indeed from the eplerenone group. We now want to know what the probability is that this patient did not experience any adverse events from the test drug eplerenone. Now from the statements, we can tell that the grand total is no longer of interest, but rather the total number of patients randomized to the eplerenone group. We could actually reword the statement as, what is the probability that a patient does not experience any adverse events, given that the selected patient is from the eplerenone group? Now this type of probability is written as such, in which the vertical line is read as given. This now reads as the probability of n given E. Recall from earlier that the grand total is no longer of interest because from the statements, we've restricted ourselves to the eplerenone group. With that, the denominator now becomes the total number of patients randomized to the eplerenone group, and the numerator are those patients in the eplerenone group that did not experience any adverse events. Our desired probability now is 0.1191. We call this type of probability conditional probability. It is a probability of an event, which in this case was not experiencing any adverse events, designated by n, given that another event, which in this case was being in a eplerenone group, designated by E, has already occurred. With conditional probabilities, the size of the group of interest is now reduced by conditions not applicable to the total group. As was demonstrated in the example, the size of the group of interest was restricted now to the number of patients randomized to the eplerenone arm. In effect, the denominator is only a subset of the total group. Now, what if we want to know the probability that a randomly selected patient from the total will be in the eplerenone group and will not experience any adverse events? Take note of how the conditions were stated. Take note as well that we now have two characteristics or events that occur simultaneously. That is, being in the eplerenone group and not having any adverse events. From the contingency table, we see that 162 patients have these two characteristics in common. The notation would now be as such. The upside down U pertains to intersection and is basically the same as the Boolean operator AND. Thus, this whole expression is read as the probability of the intersection of N and E, or the probability of N and E occurring jointly. Now, since the selection will be made from the total set of patients, the denominator is 2,729. That will now give us a probability of 0.0594. If we are to construct a Venn diagram of this probability, it will be as follows. Now let us suppose that this is the complete set, or the universe, which has the 2,729 patients to which we have data on adverse events. We then let this circle here represent the patients who are randomized to the eplerenone treatment arm. This other circle would then be for the 352 patients who did not experience any adverse events. Now take note that these two circles overlap each other. That overlap would then represent those patients from the eplerenone group who did not experience any adverse events. Now this type of probability is called joint probability, and is defined as a probability of two characteristics or events occurring together at the same point in time. In the example, these two characteristics were being in the eplerenone group and not having experienced any adverse events. Now this probability makes use of what's called the multiplication rule, which states that the joint probability is equal to the product of an appropriate marginal probability and an appropriate conditional probability. So in our example, the probability of N and E occurring jointly is equal to the marginal probability of E multiplied by the probability of N given E. Now in earlier examples, we've already determined the two terms. This gives us the same desired probability of 0.0594. Now, we mentioned in the previous slide that the joint probability, according to the multiplication rule, is equal to an appropriate marginal probability and an appropriate conditional probability. Now, earlier, we stated this, but actually, the joint probability can also be stated like this. Now, let us test the other way of stating the multiplication rule using the same contingency table. When determining the marginal probability of n, that is, the probability of not having any adverse events, we make use of the total number of patients who did not experience any adverse events, that is, 352, as a numerator. Our denominator will be the total number of patients, which is 2,729. With regards to the conditional probability term, we've restricted ourselves to the total number of patients who did not experience any adverse events. This then makes the denominator 352. Since we are interested only in that portion of patients without adverse events who were included in the eplerenone group, our denominator would then be 162. Now, making the appropriate cancellations, we eventually end up with the same probability, which is 0.0594. With that, allow me to introduce another concept, which is the concept of independent events. Now, two events are said to be independent if the outcome of one event has no effect on the outcome of the second event. A good example of independent events are coin tosses. Now, each coin toss is a perfect isolated thing, and the way it is tossed previously does not affect the subsequent tosses. The chance is simply 1 in 2 or 50%, just like any coin toss. Now, as far as our example is concerned, the two events we are interested in is a treatment group assignment and the occurrence of adverse events. Assuming that these two events are indeed independent, the occurrence of one event should not in any way affect the occurrence of the other event, though in a biological sense, this may not necessarily be the case, as we will see later. Now, if two events are indeed independent, the product of the marginal probabilities of these two events will equal the joint probability in all instances. Expressed mathematically, we get this. Conversely, if you want to show that two events are not independent, only one instance in which the product of the marginal probabilities is not equal to the joint probabilities needs to be demonstrated. Now let us show an example in the following slide. Now recall that the two events we are interested in are the treatment group assignment and the occurrence of adverse events. Under the assumption of independence, the treatment group assignment does not affect the occurrence or non-occurrence of adverse events and vice versa. Let's now focus on one possible outcome of treatment group assignment, which is being in the eplerenone group, something we earlier designated as E. Similarly, we look at one possible outcome in the occurrence of adverse events, which is having no adverse events occurring, something we earlier designated as N. Earlier as well, we were able to determine the probability of N and E occurring jointly. We now want to find out if treatment assignment and adverse events are independent by multiplying the marginal probabilities of the two outcomes we selected. Now, as we can see, although the probabilities are quite close to each other, they are still not equal. So technically, the two events of interest are not independent. This actually makes sense biologically. Since the two treatment groups would entail two different treatment modalities, we would expect different adverse events profiles depending on which treatment modality was used. We could actually use other combinations in the example, such as hyperkalemia and being in the eplerenone group, hypokalemia and being in the placebo group, and so on and so forth, in order to show that the product of the marginal probabilities is not equal to the joint probabilities. However, we need to show only one instance to prove that two events are not independent. Now that we know that these two events of interest are not independent, this formula for the multiplication rule does not apply. We instead use these formulas which we have featured earlier. These formulas are more appropriate to use when we want to determine the joint probability involving two events that are not independent. Now, let's go back to the multiplication rule from earlier. We could actually rearrange this equation algebraically into this. With that, we now have a new definition for conditional probability. The conditional probability of event A given event B is equal to the probability of event A and event B occurring jointly divided by the probability of event B provided the probability of event B is not 0. Now, let us revisit marginal probability. We earlier referred to it as the probability in which the numerator is a marginal total from a contingency table, and the denominator is a grand total. There's actually a more general way in defining marginal probability, applying the concepts we have learned earlier under joint probability. In order to do so, we need to assign all the outcomes under adverse events with their own respective letter, like so. Recall from earlier that we designated the outcome no adverse events as n, which we are preserving here. Now, let's say we would like to determine the marginal probability of a patient randomly selected from the total as being a member of the eplerenone group. One approach in determining it is by computing for the individual joint probabilities for each category or outcome under the column heading Adverse Event, which is as follows. Now we add all of these joint probabilities together and we get the same value for the marginal probability that we determined earlier. Now with that, we can define marginal probability more generally as follows. Given some variable that can be broken down into m categories designated by a sub 1, a sub 2, up to a sub I, all the way down to a sub n, and another jointly occurring variable that is broken down into n categories designated by b sub 1, b sub 2, up to b sub j, all the way down to b sub n, the marginal probability of a sub I is equal to the sum of the joint probabilities of a sub I with all the categories of b.